Today, if you want to figure out where you are, chances are you'll use one of these. But we're going to go ahead and focus on using the materials here and the sun to figure out due south, your latitude, and your longitude. Now keep in mind that our measurements of time are based on the apparent motion of the sun, the stars, and the moon. That means there's a lot of information packed into your watch.
Take, for instance, the idea of noon. Before standardized time zones, noon was simply the time of day when the sun crossed an imaginary line connecting due north and due south, called the meridian. Let's look down on the Earth from the North Pole. Here in Somerville, noon occurs when the sun is due south. In Beijing, it's the same thing. Anyhow, at local noon in the northern hemisphere, the sun is due south. At midnight, it's half a world away. We could make a clock with an hour hand that went around once every 24 hours, but most hour hands go around twice a day.
This means the hour hand moves twice as fast as the sun appears to.
Meaning, if you take your watch and point the hour hand at the sun, halfway between the hour hand and noon is due south. In the southern hemisphere, it's due north.
So the next time you need to find south, just take your watch, hold it parallel to the ground, point your hour hand at the sun, and halfway between the hour hand and noon is due south. Now, that's if you're in the northern hemisphere. Keep in mind your watch doesn't run on local time, so if daylight savings time is in effect, you'll have to subtract an hour. And thanks to standardized time zones, you'll be off by a few minutes. Plus, there's the fact that the geometry of the situation means that things will be less precise around sunrise and sunset. But you get the idea. Now, how does something like this help us find out where we are? Well, this is a sextant, and it's really just a super protractor.
You look at one object, like the horizon, through the sighting scope, and a half-mirrored piece of glass lets you line up the reflected image of some other object, like the sun, the sextant telling you the angle between the two.
You can make a similar device called a quadrant from these materials here. It's basically a protractor that we're going to affix a straw to as a sight and a string to help us find the vertical. You can print these plans out from the URL listed here. A quadrant lets you measure the angle between the horizon and an object, in this case the sun. So do not look through the sight. Instead, place an object behind the quadrant and look for the shadow cast by the straw. When the shadow is a circle, you've got the sun lined up.
Two numbers can describe every place on Earth, latitude and longitude. These are measured in degrees from two imaginary lines, the prime meridian and the equator. All points at a certain longitude are the same amount of degrees east or west of the prime meridian, and all points at a certain latitude are the same number of degrees north or south of the equator. We know from working with our watch that at noon here in Somerville, the sun is due south. That is, it falls on an imaginary line connecting north and south, a meridian. So, let's look at the noontime sun.
Keep in mind, the sun is really far away, so anyone pointing at the sun will point in the same direction.
Knowing this, if the sun were directly above the equator, we could find our latitude by simply finding the angle between the sun and overhead. That is, 90 degrees minus whatever our quadrant reads. Unfortunately, the sun doesn't stay directly over the equator. The Earth has a tilt in its axis, so over the year the sun moves above or below the equator by roughly 23 degrees. This additional angle is called declination, and we simply add or subtract it from our measurements.
Sailors used to produce books listing the sun's declination for every minute in the year, but today you can find this on the web.
We know local noon is when the sun crosses the local meridian, and you've probably noticed that a meridian is also a line of longitude. So if you know when noon happened, you already know your longitude. All we have to do is convert our time to GMT, the local time at 0 longitude. Every minute the sun covers a quarter of a degree, so if your noon took place 5 hours and 4 minutes after noon GMT, your longitude is 76 degrees west. 3 hours before GMT, 45 degrees east. Of course, we had to find local noon first. To do that, plot the midday measurements from your quadrant against your watch time. They'll make a curve, and at the top of that curve is local noon.
I'm David Colarusso for the Tabletop Explainer.
The Viking Sunstone, a lost technology of the ancient world, enabled the Vikings to cross the Atlantic and discover America. The Vikings sailed the Atlantic Ocean with ease. They had great ships. Based in small villages in the North Atlantic, the Vikings sailed to Iceland and perhaps the Americas. Archaeology has proven that the Vikings sailed and colonized the Atlantic before the compass came into use. In clear weather, they used the sun, stars, and visible coast to find their location. But what happened when the sun and the stars were not visible? Days at sea without being able to navigate could doom a ship and its crew. So without a compass, long sea journeys were likely to fail. Legend has it that the Vikings had a well-guarded secret of navigation during times of poor visibility. It was said they used a sunstone to find their position. This is a sunstone, a calcite crystal used by the Vikings to find the location of the sun. Here's how it works. Icelandic calcite, also known as optical calcite, creates a double image of an object below it by polarizing the light passing through it. Even on a cloudy, sunless day, the double image of the dot can be seen through the crystal. This was tested on a dark day when the sun's position could not be determined. Notice the blurred image when the sunstone is not in line with the sun. The crystal is moved to find the focal point. When alignment to the sun is found, the double image comes into focus and lights up. Once in focus, the dot is pointed directly at the sun and is accurate to within 1 degree. With that, a ship's position and the time of day can be determined. Is that cool or what? Is this why the Vikings were able to navigate the uncharted seas and cross the Atlantic to the Americas?
In this video, I'll be making a Stormglass, an 18th century device that can supposedly predict the weather with its unique crystal formation brought about by subtle changes in air temperature. The instructions for how this instrument is to be read for weather prediction are detailed in the video description below. I'll leave it up to you to decide how well you believe it works. Regardless of function, a Stormglass is a very beautiful device, and an excellent lesson in solubility as it relates to temperature. The components of the liquid found in a Stormglass consist of 3 solid chemicals dissolved in a solvent of ethanol and water. To keep things simple, the solvent I'll be using is 100 proof vodka, which off the shelf is already at a 50-50 ratio of water to ethanol. 300 milliliters is measured into a jar. The solid chemicals required are camphor, potassium nitrate, and ammonium chloride. Camphor is the most unusual of the 3, with a strong smell like mint or menthol. It's sold in these 1-ounce tablet packs, often as a preventative for rust in toolboxes, as the waxy chemical sublimates and can form a protective layer on steel. The contents of 1 tablet pack, weighing 28 grams, is dropped into the pre-measured solvent. Next is measured 10 grams of potassium nitrate, which is roughly equal to a full teaspoon. Another 10 grams of ammonium chloride is the final ingredient. Dissolving the solids is done by lightly heating some water into which the jar of solution is placed. The heat will increase solubility. A lid can be set loosely on top during this time, with some ice cubes above to distill any alcohol that might try to evaporate. Do not use a sealing ring or any sort of airtight lid while the jar is being heated. Doing so would cause pressure to build inside and may cause the jar to explode. Once all solids in the jar have dissolved, the burner can be turned off and the water cooled. Only after it has become cool enough to touch can the ring be safely fastened onto the jar, making it airtight. This is the final Stormglass. Don't drink this. For best results, the glass should be kept outside or in a non-climate controlled room. As the weather changes, you'll notice new crystal behavior and formations every day.
Hey guys, Backyard Scientist here. Today I'm going to show you how to do an old chemical experiment known as a tree of Saturn, or a lead crystal tree. Now, Saturn was the alchemical name for lead, and just like its silver counterpart, which was grown on a copper wire, lead is grown on a strip of zinc placed in a lead acetate solution. The first reference I found of this was in an 1882 high school chemistry book, and it gave me a little picture along with a small information on it, and again in a 1947 issue of Popular Science. So I was quite pleased when my experiment turned out to look just like that. Now, to make this solution, I dissolved 10 grams of lead acetate in 100 milliliters of water, and to this I added a small amount of zinc that I melted along with a brass nut, because brass contains some zinc. You can see that the zinc instantly blackens as it's forming lead crystals on there that are becoming apparent by 2 minutes in. And by 5 minutes in, I noticed a lot of small crystal faces on it. This is called a single displacement reaction. What's happening here is the lead acetate is reacting with the zinc to form zinc acetate and elemental lead, which deposits in the form of small crystals, which over time grow out to larger crystals and kind of form a branch-like and tree-like shape, and that's how it gets the name Tree of Lead.
Energy, lubricants, and arousal gels.
Ancient alchemists used to think that this proved that metal was alive because it spontaneously grew in the shape of a tree. Now, 24 hours later, my tree is well developed. And it has lots of big bright crystals on it, but the problem is they're kind of weak and they're fragile. You can see them swaying in the water, and I tried to take the tree out of water to kind of preserve it and save it, but when I did that, all of the leaves melted down, and it was hard to retain its original shape, as you see here. Although it does look cool, lead quickly oxidizes in air to form a gray or white coating of lead oxide on it. Now I tried this again with a penny, and I tried to put it on the bottom of the beaker, but instead, growing up, it just forms a flat mass of small crystals. Well, thanks for watching, guys. I just broke 1,000 subscribers, and that's really awesome. Keep watching my videos. Keep subscribing. It makes me really happy to do this. And check out the description for the full text of the books I mentioned. It's really cool. There's a lot of neat things in there. Bye, guys.